Hello everyone, welcome back. The last class we looked at the HLL solver, and what we did is we basically assumed that there are only two waves, SL and SR, and we ignored the contact discontinuity. Okay, and based on that we basically found this FHLL, okay, by using Rankine-Hughes condition across SL and across SR. Okay, but because you are ignoring the contact discontinuity altogether, then of course any flow which has got uh, this discontinuity will not be resolved properly, right. So, that is one of the issue of that HLL. So, later it was basically modified to HLLC solver by Toro, okay, EF Toro in 1994, and it is named as Hart-Lex one layer contact solver. So, contact stands for resolving the contact discontinuity, right. So, what we do here is that now we have the third wave, okay, which we call as S star. So, we have SL, okay, SR, and then we have now S star, which basically represents the discontinuity. These are not U plus A, U minus A and U, okay. So, like we discussed last time, that the SL and SR are basically, this is let us say minimum of UL minus AL and UR minus AR, and similarly SR was max of UL plus AL and UR plus AR, right. So, in a similar manner this SL and SR are some quantities, okay, coming from this kind of definitions, and S star is something that you have to determine, right. The other thing is that you can also take row average quantity, as we discussed earlier. It may be U hat minus A hat and U hat plus A hat also, okay. Now, how do we determine S star, and eventually what we want is F star, right. So, that we have something undisturbed, which is basically just UL, okay, some region between this and this, some region between this and this, and then some region in this region, right. So, earlier we had only 3, 1, this entire thing was this thing in 2 in HLL, and this 3. Now, we have 1, 2, 3 and 4, correct. So, again we will use this Rankine-Hughes condition, the consistency condition, okay, across SL and across SR, okay. So, we will call this as U star L, one between the S star and SL, another one is between S star and SR, which is U star R, right. So, if you apply here across this discontinuity across SL, then we will have F star L is like we did last time. So, we will have basically F star L minus F L is equal to S L U star L minus U L, right, and similarly you can write for the F R. So, these are the two expressions that you are going to get across S L and S R. Okay. Now, across the contact discontinuity, okay, we know that only density jumps, and any quantity derived from density, for example entropy, there you can see the jump there, but no, there is no jump in velocity or the pressure. There has to be continuity in these quantities. So, whatever you determine from left and right. So, in this case this is basically S star, and whatever pressure that you are getting from left and right, they should be equal to P star. Okay. So, both the pressure on the left and right should be equal, right. So, these two continuities need to be followed, and the idea is to determine the S star and the P star. Okay. So, we will basically use the first we will use the mass and momentum equation on the left side. So, like we did last time. So, now we have the mass equation here. So, that will be rho 1 u 1 minus rho 2 u 2, okay, equal to S L into rho star L minus rho L, okay, that is for mass. And then similarly, we will have a momentum, which will be basically the velocity square. So, velocity basically rho u square, right. So, this will be on the left hand side, and then you have pressure also, and then this has to be equal to S L rho star L S star minus rho L U L. Okay. So, whatever the momentum change you have here multiply by S L should be equal to this quantity that we have. Okay. So, from this from 1 you can get the value of rho star L by manipulating this equation. Okay. So, we will have rho star L and S star minus S L from here will be equal to rho L UL minus SL, right. So, then you can get this rho star L from here. Okay. So, we got the rho star L from mass equation, and now you put this value of rho star L into this momentum equation. Okay. Everything else is unknown. So, you can get the value of P star from here, right. So, by some mathematical manipulation, you basically will get this expression. Okay. So, you got the value of P star U star L U star R is equal to H star, that we already know. So, this is for the I mean, this is you are getting from the left side. Okay. Similar thing you will get from the right hand side also, right. So, this you are getting from the right hand side also. So, once you compare this left and right hand side, because they are both has to be equal, okay, you will get the value of S star. So, compare both left and right, okay, and then you will get manipulate it further and you will get the value of S star, which is basically the speed of the contact discontinuity. Okay. So, if you look at the Euler equation, you have three equation. One is the mass, momentum, and then third is the energy, right. So, in this particular case, HLLC solver, because we are also considering the jump in the contact discontinuity. So, you have to have the unique jump in the E also. That means, we are looking for something called E star L and E star R. Okay. So, first let us derive this E star L. So, like we did from mass and momentum, we got this S star. In this case, we will consider the energy and the mass equation, okay, and mass conservation, and from that you will get this E star L. Okay. So, finally, you will have basically this expression where k can represent either left or right state. Okay. So, this is in the mass, it is just 1, which is basically rho k, or it will be just rho L. And you can see one more thing, that we have this expression which can be written as eta equal to let us say if it is left, then SL minus UL by SL minus S star. Okay. So, whenever S star is equal to UL, eta becomes 1, right. So, this is basically the consistency condition, that if S star becomes UL or UR, okay, it will become, so it will become just rho L, and this will become rho L UL, right. So, if eta is equal to 1, then U star L, which is nothing but UL, that will be rho L UL, and then whatever the energy equation that you are getting from here, because this is equal to 1, right, or I can call it rho L EL, right. Similarly, if when the eta will be equal to 1, when S star equal to UL. Similarly, when S star equal to UR, okay, only small u, this small u denotes the velocity, and this capital U is basically it is a vector consisting of all three conserved variables, right. So, when S star equal to UR, again this will become 1 when k equal to R, and then it will have basically U star R is equal to UR, which is equal to rho R UR and rho R ER, right. So, this is the consistency condition. So, we got all these three expressions. So, now you know these fluxes on either side. So, you can sorry, the very conserved variables on either sides, you can write your flux scheme. So, earlier we had only in the HLL case we had SL greater than 0, and then basically these three, these are the three things that we had. Okay. Now, we have four things we have, right. So, this is SR, S star and SL. Okay. So, if SL is greater than equal to 0, then we will have basically just this FL here in between this region. Okay. So, SL is less than 0 and which is less than S star, and what we are doing it basically this is your XT curve, right. So, if you look at this curve here, so how do you get flux at any given time? So, if you this is the T and X diagram, right. So, let us say you want to find out what happens at n plus 1. right. So, this is your curve. Okay. So, this you have this region, you have this region, you have this region, and you have this region. Okay. So, we are looking at what happens x by t equal to 0 curve, okay, on this axis. So, that is what we are doing here. Right. So, we will have 4 expressions. So, second will be F L plus S L u star L minus U L, third is F R plus S R u star R minus U R, which is when S star is less than S R, okay. And finally, the S R case, which is basically just F R. So, this is F R, this is F L plus S L u star L minus U L, and this is F R plus S R u star R minus U R, right. And S L and S R are the values that we can specify based on the definitions that we discussed earlier. S star is the value that we derived, and then we also have the value of basically the last quantity, which is coming from the energy conservation, right. So, this entire thing is basically u star L or u star R, which is given here, and U L and U R you can calculate directly from the Euler's equation. So, this is what is the HLLC solver. So, this is an improvement over HLL solver, and we can see that this is a very stable solver, and works in a wide variety of cases, and it can also predict the contact discontinuity like the row scheme. Okay. Yeah. So, this is a comparison of all flux schemes. So, Lex Frederick we are using the wave estimate, the lambda was just 1, which was global max, and it was giving high dissipation. It smears all the modes significantly. In fact, it did not have any distinction between the modes. We just said that this is the maximum wave speed with which it will propagate. This is what was giving you the dissipation. In the Rozanov scheme, we basically modified this to the local max. Okay. It has got also high dissipation, but lower than the Lex Frederick. It also smears all 3 modes. Okay. Then these are the 2 schemes which are very popular scheme. HLL is it is just the 2 wave approximation of the 3 wave physical system, only SL and SR, okay, and it is good for shocks, but poor for contact discontinuities. So, HLLC and rho scheme are basically very popular schemes. The rho scheme we have basically linearized the system, okay. Instead of A we have used this A hat UL UR, okay, and we got these 3 waves which are real waves, okay, the real speeds, and it captures all the modes sharply, but needs an entropy fix, as we discussed that if you do not have an entropy fix, it will it may predict particularly in the transionic case an expansion shock, which is not physical. And HLLC has got 3 wave approximations, okay, the SL, S star and SR, okay, and it is much better than HLL, and it is almost I mean as good as rho scheme, and it is widely used, and it restores the contact discontinuity which was not coming in HLL. So, let me show you some examples. Okay. So, this is the short shock tube problem that we have been discussing, and I have shown you all examples of Rozanov, HLL, rho and HLLC. Okay. So, in this particular case you will not be able to basically differentiate all these 3 schemes, okay, because this is a kind of very benign problem. So, we have some jump in the pressure and some jump in the density in the beginning. So, I think if it is now 0.125, this is the rho, okay, and P is like 1 and 0.1, okay, and velocity is 0, okay, this is left and this is right, okay, and with time it moves on the right. So, this will be a shock, and this will be an expansion fan, and this will be a contact discontinuity, right. So, once again this is the contact discontinuity, this is the expansion fan, and this is the shock, okay, and you can see that in the density you can see all the features. If you look at velocity, then you will you won't have this feature in velocity or pressure, right. So, if you look at this region, okay, so of course, the Rozanov is very dissipative, okay, you can see everywhere, okay, but all other 3 are almost overlapping on one another. There is some difference, but very minor difference and HLL rho and HLLC, they are almost overlapping. Okay. So, although the HLL does not have this entropy or sorry, the contact discontinuity inbuilt, still it is able to predict the contact discontinuity with some dissipation. Okay. But if you go to more severe cases where you want to compare HLL and HLLC, you will see that there is a huge difference between the two. We will see some examples. Okay. Now, as I told you, this is a kind of a benign case, and there are several cases based on this Riemann problem. Okay. So, in this case we have basically the shock moving on the right, expansion on the left, okay, and that contact discontinuity in the center. You can also have the shock on the left, okay, expansion on the right, and then contact discontinuity at the center, or you can have maybe two shocks coming towards each other, colliding and going away on both the sides. Okay. And then you can also have the basically the expansions going on both the sides. Okay. That is also possible, right. So, based on these basically Toro designed several problems. Actually, they were published in different periods of time, and Toro collected these problems, and basically he proposed many basically mainly 5 benchmark test cases. So, if you look at this book Riemann solvers and numerical methods in for fluid dynamics by Toro, I think it is available as PDF. Okay. So, you will find these test cases. The first one is the short test case, okay, jump in the density and the pressure, and we have seen what happens in this particular case. Okay. Then second problem is called the 1 2 3 problem. Okay. It is basically a double rarefaction problem. So, you can see that the velocity is negative here and positive here, okay, and it creates expansion fan on both the sides. Okay. The pressure and density are same on both the sides, but the velocity is one on the left hand side going on the left, another is on the right side of the diaphragm, it is going on the right with very high speed. So, you will have two rarefactions waves getting created on left and right. Okay. Then there are cases 3 and 4, which are basically cases of blast wave problem. So, basically a left blast wave, right blast wave problem, and this is proposed by Woodward and Colella in 1984. Okay. So, if you look at this particular case, there is a very high jump in the pressure, okay, very high pressure on the left and very low pressure on the right. So, it will create basically very strong shock, okay, and this basically tests the stability in the hypersonic shocks. Okay. This is the left blast wave, and in the second case, which is basically extension of this. So, now you take this case here on the left, and then you put a jump on the pressure on the right. Okay. This is the right blast wave. Okay. So, now there will be shock which will be traveling on the left, again this particular case, because the jump is the high pressure on the right hand side. And finally, the collision problem, where which is basically a combination of. So, we have a shock which is going on the right in this case, okay, and there is shock which is going on the left in this case, and if you put them together, this is the right shock from this and this is the left shock from this, okay, and then they will basically collide, and after the collision the shocks will move in the opposite direction, right. So, this is a combination of test 3 and test 4, and this is shock collision case. So, these tests have been created to look at which numerical scheme is better and which numerical schemes fail under what condition, right. So, short shock tube we have already seen. Let me show you, okay, before you go to description of all these test cases, there are actually some more cases which I have picked up for you. Okay, there is one thing called modified sort. In this modified sort, what we do is just we assign some velocity on the left hand side. Okay. Then we have case of isolated contact discontinuity. Okay, in this case it is actually a classical case where we can differentiate between HLL and HLLC. Okay, so what we have is we have only the density jump. Okay, all other things are same. Okay, so this is basically a stationary contact discontinuity. Okay, the velocities are 0 on both the sides, and you want to see what happens with time. And then this contact discontinuity can advect. So, you have basically some speed UL and UR, okay, and this is again there is a jump in density. Okay, you can have 1.0, 0.1 here, or 1.0 and 0.1 here also. Okay, I mean this is the case that, I mean, you can solve this also using exact demand problem, and then you can compare. And then the case that we had this the Toro's case that we had, this collision case. Okay, similar to this, we have the parameters which are modified. Okay, so very high jump in the the pressure. Okay, in fact it should be modified case 3. Okay, the cost Toro 3, not Toro 5. Okay, so this is modified Toro 3. Okay, and the pressure and the velocity remains the same on either side. Sorry, the density and the velocity remains the same on the other side, and there is a huge jump in the pressure. Okay, so this is a high Mach contact. Okay, contact swept at very high speed. Okay, then we have this sonic rarefaction case. Again, this in this particular case you can have this -1 and 1. Earlier we had -2 and 2. This is again creating 2 expansion fan. Okay, and in this, if you do not use this entropy fix, you will get expansion shocks in row. Okay, this also the density, you can say the right hand side is the velocities are all 0 0 0. So, this is basically kind of 0 density state, it is vacuum state, and in fact many of the continuum solver fails here because the density is very close to 0, the pressure is very close to 0, your energy goes very close to 0, and then you might lose if the scheme is not positivity preserving. That means if there are fluctuations due to the scheme and the density goes negative or the pressure goes negative, then solution will get killed. Okay, so that is also a peak vacuum test. And then we have basically tests like slow moving shock. Okay, this is basically you can do it for mostly in 2D problem. Okay, so in this case a shock moving at some speed. Okay, and you can test for the post shock noise. So, let me take you through some of these cases. I will not be able to discuss all of these. Okay, so these are the first Toro 5 tests. Okay, there are 5 tests. So, this is short case. Okay, we have already discussed in great detail. This is the 1 2 3 case, and as I told you, so there is one expansion wave moving on the left between this to this. Okay, between this and this, and there is another one which is moving on the right. Okay, and there is a contact discontinuity, but you cannot see, these are all density contours. Okay, you cannot see because the values are similar on both the sides, the density values. And then you have this test 3, which is the extreme pressure jump, and you can see that because of this very high pressure jump, the density which was only 1 in the beginning, it can go to as high as 6 here. Okay, and you will have basically the shocks, there is an expansion fan here, there is a shock here, and there is a contact discontinuity here. So, this is extreme case of what you say is this one, the short problem, except that the density is same on both the sides. Okay, on extreme left and extreme right. And then this is the this test 4, which is the blast wave right hand side, the right blast wave. I will correct it when I circulate this PPT with you. Okay, this is not the one. Okay, this is in fact this is the test Toro 5, this is the one. Okay, where we have given this value, the 2 shocks which are colliding, and then after the collision basically this is going on the right. Okay, there is one shock here, there is another shock here, and there is a contact discontinuity here. Okay, and this is opposite to case 3. These two together are the blast wave problem. Okay, so here you can see that shock is moving on the left, expansion moving on the right, and then there is a contact discontinuity here. Right. So, these are the 5 test cases, and let us evaluate how our solvers, which are basically, so I will not discuss about Ruzono, because as we discussed, this is a very dissipative solver. So, we will discuss HLL, HLLC and the row scheme for these problems. Okay, so this is the usual one, we have seen this is a short shock tube, and I have basically compared the row HLL, HLLC and exact here, and I plotted the density, velocity, pressure, internal energy, and you can note that in the internal energy also you can see this contact discontinuity. Okay, and expansion very well. Okay, and the shock, and this speed that you are getting because the shock is moving on the right. Okay, so it is basically disturbing the air here, and because of that you will have some increase in the velocity. So, otherwise the velocity is 0 on both the sides. So, this is taken at time equal to 0.25. So, which is within the time that it does not cross the right boundary or the left boundary. Okay. So, again you can see that these schemes are first order. So, contact discontinuity is not resolved properly, okay, in all these schemes rho, HLL or HLLC. Okay, and the exact should be, it should be a vertical line, but it is smeared out here. Okay, and same thing you can note in the energy also. Okay. Now, let us go to the test 2, which is really a test of flow in a vacuum, okay, because the density goes very close to 0. Okay. So, when I tried running this case with rho solver, although I have written rho here, there are no results of rho here. The reason for that is that it is an extreme case for rho, and you need a I mean, if you want to use rho, then you have to use a extreme entropy fix for this to run, because you can have the density going negative or the pressure going negative, okay, in this particular case, right. So, so we have gotten results with HLL and HLLC. So, they work in this particular case, even if the case is near vacuum, and there are two rarefactions here. Okay, so, there are two right and left moving expansion waves, and there is one contact discontinuity between this to this. It is invisible because same pressure and rho on the both the sides. So, and this is a difficult case for rho. Okay, and these are different quantities. You can see this is velocity. Okay, the pressure. So, pressure also has similar thing in the expansion. Okay, and this is the velocity. Okay, and finally, this is the internal energy. Near the this region where there is a contact discontinuity, there is some mismatch with the solver here, okay, compared to what you get from the exact Riemann solution. So, whatever the black lines that you see, these are coming from exact Riemann solution by solving the using the Newton option. So, you guess a P star, okay, and try to calculate this U star L, U star R, match both of them and get that P star for which both are matching, okay, and then you calculate the U star again. So, so this is an iterative approach. So, this is what is solved to solve all these problems. Of course, you need to have a very good guess for P star to get the solutions right. Okay. This is the Toro case 3, where it is an extreme pressure jump. So, 1000 versus let me see if I have that plot. Yeah. So, this is 1000 versus 0.01, okay, on the right hand side, okay, and because of that you will have basically a very strong shock moving on the right, okay, an expansion on the left, okay, and there is a contact discontinuity here, and you can see that I mean even the HLC solver, because this is a really an extreme condition, it is not able to match this very well. Okay. So, in the next I have compared this with different solvers, and I think rho also worked for this particular case, okay, and you can see that all of them behave nearly in a similar manner. Okay. Same thing, that the difference that you have in their contact discontinuity, you can see it here also. The shocks are predicted pretty well, but there is a huge dissipation in the contact discontinuity, okay, for all the examples that we have discussed. Okay. Now, this is the Toro 4, where you have let me see the pressure, that will tell you. So, this is 0.01 on the left and 100 on the right. Okay. So, this is also a strong shock, but weaker than what we had from 1000 to 0.01, right. So, if you look at in this case also, in the density curve, I show the density curve in a blown up picture, because here you can see the differences pretty well. You can also see where the whether the scheme is able to resolve the contact discontinuity, and you can see in this particular case also the shock resolved well, but the contact discontinuity you have some issues here, and then expansion and all are resolved pretty well. Okay. So, this is the classic case of shocks. I mean, this is reverse of short shock tube, or just shock tube, where the shock is moving on the left and the expansion fund moving on the right, and there is a huge jump between the pressures on left and right in the beginning, right. And this is the final case where we have uh, basically the two shocks colliding, and because of the collision they will move in the opposite direction. Okay. So, this is one shock, this is another shock, and then there is a contact discontinuity here. Okay. Again there are issues in the contact discontinuity. In fact, you can see the rho is doing slightly better compared to HLL and HLLC in this, and HLLC was also doing slightly better. There is a green curve here. Okay. And the red one or the this orange one is slightly worse than what you get from HLLC or rho. Okay. If we look at the pressure and the velocity, there is no contact discontinuity. So, you cannot find the difference that much. Okay. So, they predict the shock very well. Okay. Finally, this is the modified sort problem. So, here the only difference is that we have given some velocity on the left, and the same, I mean there is no new comment here. The contact discontinuity is not very well predicted, and then we have basically some dissipation in the expansion region also, but shocks are predicted pretty well. Again, this is the case that I was trying to say. This is the isolated contact discontinuity, where you have only the jump in the density. Okay. And you can see that if you look at this is the blown up image, and if you look at the HLL curve, this is very diffusive, and if you just include this HL, I mean the contact part in HLL, this is how you will see. This is the contact discontinuity. This is a stationary contact discontinuity. There is no shock, there is no expansion fin in this particular case. Okay. So, this is what I was trying to say, that when you use this HLLC or the 3-wave description of the problem, you will be able to resolve the contact discontinuity in a much better manner. Okay. And this is the advected CD part, where you have basically some velocity also, okay, and some pressure also, and there is a contact discontinuity which is basically getting advected. Okay. So, here also I think HLLC gives a better prediction of the contact discontinuity compared to what we have from the HLLC gives better prediction than HLL. Okay. So, we have seen comparison of these approaches for multiple problems, and I have not shown for a few problems, and I would suggest that you go back and try using these cases for all these problems also, which I have not discussed. Okay. You can just modify the code and give those boundary conditions on left and right, and you can see how it is evolving and how does it compare to the Riemann problem, right. So, these are the benchmark cases for 1D. If you go to 2D, there are some other issues with rho scheme. For example, you will get something called carbuncle phenomena, which we will probably discuss in the later classes. Okay. Yeah. So, this is where I will end, and in the next class I am going to discuss high order scheme. So, till now what we saw, so is basically this is the first order, and you can see that near the expansion and near the contact discontinuity you have some error, okay, due to the dissipation, due to the smearing out. If you increase the order, okay, here I have used second order. So, there is a reconstruction scheme called muscle. This is basically a kind of TVD scheme that we have discussed earlier, and then TVD scheme, it has to be accompanied by a limiter. Okay, in this case it is a min mod limiter, and you can see the solutions become very well. Okay, they are much better compared to what we get from the first order. So, we are going to discuss this in the next class, and we will discuss some of the high resolution schemes as well as the limiter to basically resolve these flow features better. So, we will discuss that in the next class. Thank you.